So vibration and waves will do also another exercise. This exercise is from the guide and the back. So we have two microphones, M1 and M2, that are set on the axis of a speaker H and separated by a distance T. The speaker emits sound of a frequency F. The sound wave captured by the microphones are visualized by an oscilloscope. So نلاحظ here we have three screen of the oscilloscope, a three figure. M1 is fixed and we move M2 slowly. So now M1 is here at this place and M2 is moved slowly along the axis of the speaker. In the figures below, we give the different oscillograms obtained for three successive positions of M2. So first of all, let's understand what do these oscillograms mean. So أول شيء نلاحظ إنه when M1 and M2 were at certain distance, let's suppose for example here, we noticed that these two microphones were in phase. This is in the part figure 1. This is the figure 1. And then we start moving the microphone M2. So we obtain, this will be the figure 2. And then we move it another time and then we will obtain figure 3. And for each distance between M1 and M2, this is for a distance 340 millimeter, we have this figure. For the other distance of 374 millimeter, yani for example, it's a silent microphone here, we have also another figure. And for the third distance, we have also, for the third figure, we have also a distance of 408 millimeter. Now, the horizontal sensitivity of the oscilloscope is SH equal 50 microsecond per division. This one, if we have to use it. And the vertical sensitivity on the two channels are equal. So we'll start with a question. How does the oscilloscope show that the frequency of the sound is independent of the position of the microphone M1 and M2? When I'm talking here about the frequency, نحن بنعرف إنه على oscilloscope I cannot see the frequency. What I can see is the period. What I can calculate is the period, which is the time for one cycle. So لما عم يسألني show that the frequency is independent of the position, it's as if he's asking me show that the frequency in each of these figures is the same. But since أنا ما في طلع frequency on the figure, what I can find is the period. So it's as if he's asking me to verify that the period is the same. Now, how to verify that the period is the same before we calculate it? We know that the period is the time needed for one cycle. So if I look here at the first figure, for example, this is a cycle, this is one complete cycle here. So I notice بلاحظ إنه كم square عندي 1, 2, 3, 4. So I have 4 division. So the period here, in order to find it, we have 4 division. Now let's look at the second figure. So when I moved the M2, بلاحظ هل تغيرت البيريد? So let's see, this is here one cycle. So if I want to measure, I will have 1, 2, 3, 4 كمان 4 division. ونفس الشيء وين؟ نفس الشيء بتالت figure. If I notice here, we also have 1, 2, 3, 4 division. So this means we have the same number of division in order to find the period. So since here we have the period, since if we want to verify here, since the period is the same, in the three figures, this means that the frequency is the same since I have, so this means that the frequency is the same. Since it's the same, this means it's independent of the position. يعني شو ما كانت عندي البوزيشن تبع two microphone عم بيطلع عندي same the period, this means same frequency. So frequency is the same. Now, since we have the relation that F equal 1 over T. Now, the question is to calculate this frequency. In order to calculate the frequency, we have to calculate T. So how do we calculate T? T is equal to the horizontal sensitivity, which means it's the scale along the x-axis multiplied by the number of division, and this is what I call x. So the horizontal sensitivity is already given, it's 50 microsecond per division, but I have to multiply it by 10 to the power negative 6, multiplied by x, which is the number of division. Now, if I notice here, I have 1, 2, 3, 4 division for the period, so it will be equals to 4. Then I'll get here, it's 200 times 10 to the power negative 6 second. Now I can calculate the frequency. So we'll say that the frequency equal 1 over t. So it's equal 1 over 200 multiplied by 10 to the power negative 6, which will be equal, so here I have, it's 1 over 2, which is equal to 0 0.5. So it will be 0 0.5 multiplied by 10 to the power 4 hertz. Let's continue the question. Part 2. What can you say about the points at which M1 and M2 vibrate in phase when D equals 374 millimeter? So here the question, what can you say about the vibratory state of M1 and M2 in where the distance is, so where the distance is 374 millimeter. So if I notice in the figure 2, so this is part 2, I have when the first one is at the maximum, when A is at the maximum, we have B is on the minimum. So this means these two oscillograms are in antiphase. So when A is at maximum, we have B at minimum, which means that they vibrate in antiphase. So هيك بنكون عرفنا إنه for a distance of they vibrate in antiphase for a distance for D equal 374 millimeter. So قدرنا نعرف لما طلعنا على الفيجر لما أول وحدة at the maximum, the second is on the minimum, so we can know that they are in antiphase. Now in the part 3, which of the oscillograms A or B is that corresponding to the microphone M2? Now نحن عرفنا إنه that M2 is moving away from the microphone, sorry, from the loudspeaker. So نحن شو عم نعمل؟ نحن عم نبعد we are moving away, okay, the microphone. When we move away the microphone, if this is the loudspeaker, when I move away the microphone, this is M2, منطقيا and what will happen? الvolume تبع sound will decrease. And we know that the volume of the sound, this means the amplitude on the figure. So if I notice here on the figure, I notice that the amplitude which is decreasing is that of the oscillogram B. So this means that the oscillogram B corresponds to the microphone M2. So here again, M2 is moving away from the loudspeaker, implies the amplitude of the sound will decrease, which correspond to oscillogram B. Now, part 4, the oscillograms A and B in the figures 1 and 3 are in phase. Why? So if I look at the figure 1 and at the figure 3, I notice that when A is on the maximum, B also is on the maximum. When A is on the minimum, B also is on the minimum. إن كان بالfigure 1 or بالfigure 3, which means that A and B in these figures are in phase. So here, in figure 1 and 3, we notice that when A is on maximum, B also is on maximum. And when A is on a minimum, B also is on minimum, which means that A and B in these figures are in phase. So A and B are in phase. Now, let's continue the number 5. Calculate the wavelength. So السؤال we have to find lambda is equal to how much? emitted by the speaker, and then I can deduce the speed of the sound in air. Now هون لنطلع اللامدا in the strategy of thinking, I have first to think about the given, and then I can think about the formula, and then if I have a law, I will think about the law of the principle. Now here, let's think about the given. In the given, we have a graphs. So هون المفترض ننتبه له إنه when I was at this distance, when the two microphones were at this distance, they were in phase. Then بلشوا يصيروا in antiphase, then صاروا again in phase. So إذا بلاحظ from here to here, this is what I say again, يعني just directly after in phase. So they were in phase and they become again in phase, okay, for only a one time, okay, ما قطع عندي مرتين، قطع عندي بس مرة واحدة. Then they are in phase again, which means that lambda is simply, ولما بقول again, this means we only have one cycle that's passed. So this means that the distance between the two microphones is equal to this lambda. So لكن هون, since it was in phase, for I name it D1 equal 340 millimeter. Okay, it was when I say it was in phase, this means A and B are in phase, we're in phase, and they, A and B, in phase. Again, for D2 equal to 408 millimeter. So بما إنه again implies we only have one cycle passed. So one cycle, this means the distance between them is lambda. So in order to find the distance between them, قد ايه انا مشيتها لهيدي شو صار في عندي distance بيناتهم, then I can say directly that lambda is equal to D2 minus D1, which is equal to 408 and minus 340, which is equal to 68 millimeter. Now the question is to find the speed. So we know that the speed V equal lambda multiplied by F. We have lambda in millimeters, so رح نحولها. It will be 68 times 10 to the power negative 3 meter. And the frequency طلعت معنا 0.5 multiplied by 10 to the power 4. So which means it's equal to 340 meter per second. And this will be the speed of the sound in air.